Okay, so off we go. Here's where we were last time. We were talking about notations for partial derivatives, and it's a little bit weird, to be fair. Right now, this kind of looks like a Leibniz notation for a regular derivative, but it's importantly different, and again, you do have to be really careful. That symbol is not a D. You can't choose to use a D instead. That literally means something else. It is required that you use the proper notation. Likewise, it's not a lowercase Greek letter delta. The way see how it flips over to the right at the top. Again, that makes it a different thing, not equivalent, not acceptable. So do make sure you use the right notation. There's this Newton notation, Newton-like, you might say, notation, where you just list this as a subscript which variable you're taking the partial with respect to. Has its moments where it's useful. I think most of the time that's probably the better notation, but there are some situations where that's really nice as well. Okay. All right, so so let's do one. First example, we're going to start with one that looks really hard. Look at this. It's a product of three factors, one of which is a composition, and there's all sorts of ugliness involved. There's cotangents and exponentials. Yikes, this looks like a hard one. It's not. This is an easy one because we're taking the partial with respect to y. Very importantly, remember, when you're taking a partial derivative, the very first thing you do is you set all the other variables equal to constants. So y remains a variable, but x we will treat as a constant, z we will treat as a constant. That means, well, if x is a constant, then e to the x is a constant, and furthermore, x squared is a constant, but that z is a constant too. That means that exponential is a constant. That means this product is a constant. That means this whole thing here, all constant. So what we actually have here is we're taking a y partial of constant times y squared. And that's easy, right? Take the derivative with respect to y of y squared. You just get 2y, and all the multiplicative constants there just come along for the ride. That's how multiplicative constants work. We're done. Simple as that. Everybody see how this works? Everybody happy? All right. Yeah, exactly. So I nominate partial derivatives to be the easiest derivatives to compute, including single variable derivatives, because I don't have to deal with everything. I get to just treat massive fractions of my expression at constants. It's better even than single variable derivatives from a convenience point of view. So I think that's nice. Okay, so let's do a couple other real quick. I'm not going to work through the details on these. I'm going to assume that y'all are strong with your single variable derivatives. If that's not the case, you might want to brush up, etc. Right? But anyway, we're going to assume that you're strong on single variable. So let's take the x partial here. And again, it looks hard. It looks like a function to the power of a function, but it's not. Because x is the variable, that means y is a constant, that means y squared is a constant. That means I have here nothing more than a polynomial to the power of a constant. And y'all remember how the power rule works, right? So, chain rule, power rule, boring old single variable differentiation. And it feels wrong, right? Because it feels like, can I really do this whole thing when that's a function? And the answer is, yeah, because for the purposes of what we're doing here, it's not a function. Looks like a function. Constant. Everybody happy? Okay. Equivalently convenient. Let's take the z partial of this great big thing. Keeping in mind that means x and y are constants. That means this whole base is a constant. So this is nothing more than constant to the power of z. And again, y'all remember old rules from single variable calculus about how to take the derivative of exponentials. Okay. And again, brush up on those details if you're a little rusty. Okay, let's summarize real quick what we have here. We have a process that we've described, seemingly motivated by self-interest of convenience. Not very mathematically impressive. I feel like this would be an easy thing to do is not a good mathematical argument, right? We've developed a notation. We've applied this method, but so what, right? Just because you define something doesn't mean that it is useful. I can define all sorts of nonsense that's super convenient and meaningless, right? So what we have to worry about now is, convenient though this is this actually good for anything? Does this mean anything natural? Does it have a natural geometric interpretation? Anything along those lines, right? And it's going to turn out, yeah, there's some great answers to this question. So we are going to talk about what the geometric interpretations are. And again, the very first thing I want to point out, always you have to worry about this. If you want to know how to interpret anything geometrically, it depends on what kind of a picture you're looking at. And how you interpret something in the context of a graph is going to be very different from how you will interpret that thing in the context of level sets. So we've got to be explicit about that. What y'all have to do is, as we go through and talk about these different interpretations, make sure to keep a partition in your mind of, you're going to develop your calculus of graphs over here, and you're going to develop your calculus of level sets in a completely different area of your brain, and then your calculus of parameterizations, or the literal pictures that we talked about. Whatever, all of these interpretations, keep them separate in your mind. Because they are completely different. Okay, so here we go. We're going to start with graphs arbitrarily, and keep in mind, if you're looking at a graph means you're going to set your function equal to a new variable. Here we'll call it z. Right, so we're looking here now at a graph of this function of two variables. Keep in mind the domain when you're drawing graphs a function of two variables we typically think of as being the xy plane, and then the target here we typically think of as being sort of the z-axis, if you will. And we're going to try to make geometric sense now out of taking a partial with respect to y at this point AB in the domain. So what on this picture would a partial derivative look like? So good news, we have a process for computing these y partials. It's a two-step process, and as it turns out, each of those two steps, we're going to be able to draw easy geometric pictures of those two steps, and putting that together, we're going to instantly get a geometric interpretation of this. Okay, so first step. Oh, and let me hit this button to... There we have more space. Don't forget, when you're taking a partial, you fix all the other variables. Now we're taking a y partial, and that means that we're going to fix the other variables, that being just x. That means x has to stay a constant. Of course, it started off with value a, because we're at this point a comma b, and so fixing x means that we're going to fix x as a, and of course that gives us this vertical plane like so. Right, and you can think then about how does our surface here, that keep in mind our surface being a graph, right? What happens when you take this graph surface and look at how it looks in this plane? We're just taking a slice then, let's vertical slice of our surface by that plane, and what that gives us then is a curve. Everybody good? Okay, now real quick, let's talk about this plane. Here's an easy point to mess up. This is a plane where we're fixing a value of x. What is a little confusing is that means that the plane points in the y direction. And it's just semantically easy to kind of, oh, wait a second, which way does it go? Y is the variable, x is the constant. The plane is defined with the variable x in the equation, and you just have to, don't try to memorize your way out of this point, right? Make sure to interpret things geometrically, and the plane x equals a, here it is, x being set a constant, points in the y direction. Everybody good? Okay, next step. This resulting single variable function, and by the way, this cross section that we're looking at, that is the graph of our single variable function, which we are then going to take the derivative of with respect to y. In other words, as we move in that direction, and taking a derivative when you're looking at a graph, which we are, just means slope of the tangent line. So that's the answer. This is the geometric interpretation of partial with respect to y. Partial with respect to y, slope of the tangent line, very familiar, very relatable, right? That's exactly kind of what we were hoping this would be. After all, we're taking a derivative of sorts and interpreting derivatives on graphs, and in a single variable, that was literally slope of the tangent line. So good news, yes, this partial derivative, slope of the tangent line. You just got to keep in mind the little details. Okay, I don't know why it does that sometimes. Look, it's just switched. Weird. Let me just confirm real quick that we're still recording. I don't know why it did the... Yeah, it looks good. Sorry about that. Okay, yeah. So the two little asterisks. Don't forget, yes, partial derivative, slope of the tangent line to the graph. This only makes sense if you're talking about graphs. And secondly, there's a bunch of tangent lines. Right? This is, in fact, an entire surface. You could imagine lots of different lines that are tangent to that surface. This is specifically the slope of the tangent line that points in the y direction. Okay. All right, now here's an exercise for y'all to do for yourselves. I think it's very doable. You can copycat heavily from what we just argued, and that is persuade yourself that the x partial is the slope of the tangent line to the graph in the x direction. It's exactly what you would expect by what you might call semantical analogy, right? But I want y'all to think through the mathematical analogy. Think through, how do you draw the diagram? How is it different? How is it the same? Think through the geometry. Make sure that you buy this mathematically. Okay. Okay, all that's graphs. Let's think about one of our other pictures. Again, graphs are awkward. They're dimensionally expensive. We very often just can't afford it dimensionally. We don't have enough dimensions to draw graphs very often, right? Such as, for example, in a case like this, I can't draw the graph of this function here. 3 inputs, 1 output, losing, right? So, okay, we can draw the literal picture. We've talked about this before, right? You literally draw the domain and the target. How would I make sense out of partial derivative in this context? So the first thing to keep in mind, partial derivative means y is the only variable. That means x and z are fixed. That means x is and shall remain a, and z is and shall remain c, which means that I'm kind of stuck on this line right here, because x and z aren't allowed to change. Okay, so, and then as I do that, how am I going to make sense out of this partial derivative? I'm going to remind y'all of another interpretation from Calc 1, right? Different way to think about single variable derivatives is the relationship between input changes and output changes, right? It's the factor that you multiply by input change to get output change. And so I'm just going to write that down exactly, that the input change, how much I move from this point, keeping in mind that I can only move in the y direction. I'm going to call that dy, right? And then there's a resulting change in the output of the function. I'm going to call that df. So how do we geometrically interpret partial derivative then on this picture? Well, I can't point to it. It's not like a place in the picture or something that I can see in this picture, but I can see evidence of it. I can see what it does because it's the thing that I multiply by this input change to get that output change. So here we're interpreting partial derivative as being a factor. Yeah.
You said we're like stuck on a line.
Yeah.
Where is that line? I don't know.
Yeah. So by assumption, we're interested in this partial derivative at some point. That point, I'm going to say, has a, b, c. X and z aren't allowed to change. That means x is stuck at a, z is stuck at c, and that in fact defines a line.
Oh, okay.
Yeah, does that make sense?
Yeah.
And by the way, notice, conveniently as it should be, that line defined by x and a not changing is a line that is exactly in the y direction. Yeah. Good. Okay, so different picture, right? Oh, yeah.
I can't seem to understand why we're, like, can you just please go over the df equals the partial times dy?
Yeah, this is just a flashback to some old information about single variable derivatives. That single variable derivatives are what you multiply by input change to get output change. And I'm just making the observation that once we set x and z to be constants, in fact, we do have a single variable function because y is the only remaining variable. Yeah, sure. Yep.
Can you repeat what you said, the input and output was?
So one more time.
What was the input and output again?
Yeah, so the idea is that we're moving in the domain by some amount. That's, of course, in the y direction because it's the only thing that's allowed to change. So that's dy is our input change. And then the point is the function called f changes by some amount, so I call that df. Yeah. Okay, next picture, level sets. This one's particularly confusing and dangerous because a level set, let's take a quick look at, let's say, this level set right here that I have highlighted in purple there. That level set, it's a curve. Sometimes graphs are curves, and it's going to be tempting, right? You're going to have this kind of impulse to reason as follows, and that is to say, there's some sort of a derivative or whatever, and here's a curve, and isn't derivative supposed to be the slope of the curve? Isn't that just how derivatives work? Right, that's your Calc 1 little shoulder devil talking to you there. Right, does everybody see the temptation, right? It's a curve, we're talking of derivative, why wouldn't it just be the slope? Well, it's not the slope because this is not a graph. This is a level set. Everything in Calc 1 that you learned about derivatives being slopes, that is exclusively for graphs. And they don't make a big deal out of that in Calc 1 because everything in Calc 1 is a graph, right? It's an unnecessary thing to say in a Calc 1 class. So here you just have to remind yourself this has nothing to do with graphs and no derivative when you're talking about level sets tells you the slope of that graph. It just doesn't. So here's the way I like to think about this, and that is remind yourself that level sets can be thought of as contour lines, right? So I literally like to think of myself as on a hike, and that's me. And the curves here, these are the contour lines that represent the mountain that I'm climbing around on. And let's just think about, okay, well, how steep would my hike be if I want to make sense out of the x partial, if I go in the x direction, and how steep is that hike? And I got to tell you, that looks really steep. And look how close those contour lines are to each other. Each one of those contour lines is, it could be like 40 feet, let's say, as it was on the map we looked at previously. That just looks like it's pretty steep. So that x partial, I don't know exactly how large. I would need scale. I would need to know what are my units here and what's the separation between these contour lines, etc. So I can't tell you quantitatively exactly how large, but I feel like that looks kind of large, right? And now by contrast, if I were going in the y direction, okay, I'm going that way. Fine. That doesn't look that bad. You know, look, I get to cover quite a bit of horizontal distance here in order to pass one contour line as opposed to very little distance. going in the x direction. So this looks like a much more gentle hike. It doesn't look that steep. If I were to imagine the graph corresponding to these level sets, right? On the graph, this would not be a steep cross-section. And so I infer that the y partial would be small, relatively small. And again, I can't be precise. We don't have scale set up here. That's not really the point exactly, right? The partial derivatives, again, don't explicitly manifest on this picture. But you can glean some loose information about them by just looking at the kind of the nature of the contour lines and how they relate to each other in these different directions. Is everybody okay? Okay. All right. Okay. New thing we're going to talk about, linear approximations. There's a couple of little annoying points I have to talk about. First of all, wrong button. Linear approximations are not linear. That's weird. Why do we call them linear approximations if they're not linear? Yeah, it's a good question. And there's a somewhat of an answer to that question that I'll get to in a little bit. Anyway, just keep that in mind. The other thing that I want to kind of sweep under the rug here, I am going to assume. And this is going to prove to be a poor assumption in a bit. We'll talk about the bad news later, but I'm going to assume, just to get the ball rolling, that the linear approximation exists. And we'll worry later about how you can tell if it actually exists, and therefore whether any of what we're about to write down actually makes any sense at all. Okay. All right. So with all of that said, let me just remind y'all from single variable calculus, don't forget about this formula. I'm sure y'all all remember that. You probably know this by various different names. For the moment, I'm going to just say this is what we call the linear approximation. And why do we care about the linear approximation? It's different points of view. The one I'm going to push here, because I think it's particularly convenient, is we like this because this is the unique polynomial, degree 1 polynomial, that agrees with my given function f at the point A in terms of its value, and it also agrees with the given function f at the point A in terms of derivative. So this is what I'm going to call a mimic. Right? The reason we care about this formula is because in terms of value and derivative, this is just mimicking the function f at the point A. Is that cool? Seems like a reasonable characterization of the linear approximation. It's copycatting what it's trying to approximate. Okay, now I want to make sure y'all know how to prove this. I think this is a pretty straightforward argument. You may have no problems with it. The green item here is pretty straightforward. Just literally plug in x equals a, and you plug it in, and boom, you get f of a, no problem. That's the easy part. How do we prove the second part here, that L prime at a is f prime at a? Well, you literally take this expression, that's L, you take its derivative, and then you plug in x equals a. So we're just literally going to plug and chug on that. The thing you have to keep in mind when you do that is don't forget that this is a constant. All right, a lot of students will forget about that. This is not f prime of x. Very importantly, this is f prime of a. So a is fixed and doesn't move. So whatever the f prime function is, when you evaluate it at a, is fixed. Doesn't move. Some value. So keep that in mind. As you take the derivative of this function, don't forget to treat that as a constant because it is literally a constant. Okay, make sure you can do this. Make sure that you can confirm both of these properties. Okay, and with that in mind as our model, let's try to do the same sort of thing for multivariable. And I claim that here's what works. I emphasize, I'm not deriving this. I'm just noting, hey, you see that thing that I just pulled out of thin air? Right? That, I claim, has these same two properties. I claim that that expression has the same value as f at the point A. Again, plug it in. See, it works. You can do that on your own time there at some point. And then likewise, it's got all the same, oh gosh, now I have to think about how to phrase this. We want to do a multivariable version of saying it's got the same derivative, but now we're in a multivariable context. Now there's several input variables. So I'm going to have to say all of the partial derivatives. That's not just that there is a single derivative. There's a bunch of partial derivatives. And so I think the analogous requirement should be that all of those partials agree. Okay. So again, this is something that I want you all to check. Make sure you can do this. Do keep in mind, I'll give you the same reminder, this expression right here is a constant. And the reason why, oh, by the way, just as a notational point, you might not have seen, if you haven't seen the following notation, here's what it means. This vertical line right here just says, look, everything to the left of it, that's some function that I want to evaluate at this point down here. That's the subscript. I use this sometimes. It's very common, standard notation. I didn't make it up. When there's a parenthesis that follows, here, for example, I'm multiplying this thing times xn minus an. It just looks weird to have something and then parentheses and parentheses, but those parentheses are doing different things. I just find it's confusing looking. So I'm using this vertical bar with a subscript just to avoid that visual awkwardness. All it means is evaluating this expression at that point. And again, a being a constant, when you plug it into whatever expression, you get a constant. So as you go through, 2 seconds, as you go through and do this, as you go through and compute these various partials, trying to confirm, for example, that the x1 partial of L at A is the x1 partial of F at A. As you do that, keep in mind that this, what I have in gray, is a constant. Yeah?
Is it always going to be to R1, like Rn to R1?
Oh, that's all we're considering right now. That's a great question. So let me point that out. We are considering for now just real valued only for the moment. This equation that I've written down here only works for real valued functions. Yeah. Right. Okay. Okay, so again, good little practice problem. Make sure you can do this, but I have an orange down here. Thus confirming then, by the way, once you've done that confirmation, that confirms that this formula does kind of what we would want it to do. It's a good mimic of F. Okay. All right, let's do a plug and chug. Oh, no, I'm sorry, I got ahead of myself. Let's talk about notation a little bit. You look at this formula, and it goes almost all the way across the page. It's a little bulky. And I claim there's a way to not only make it shorter, but actually to recognize there's a powerful expression inside of this formula that's very valuable to recognize, because when you can recognize a whole bunch of stuff as being some operation that you know theorems about, that means that you can then use those theorems when you need to. Very, very handy. So in particular, here's what I'm talking about. I claim this I can rewrite in a very, very nice way by simply noting that what I have here is a bunch of factors being being multiplied by a bunch of other factors, and I am then adding the products of those factors. Where have we seen that expression before? And it's a dot product. That's what a dot product looks like. Right? So I'm going to be able to rewrite this as a dot product. Now, in order to do so, in order to be able to rewrite this as I claim that, I have to notice, first of all, that what I have in blue here, right, these blue factors, those are literally the coordinates of the vector x minus a. So I can see that x minus a is one of the vectors in this dot product. These other factors here, the various different partials, that's not something that we really recognize. We don't have a pre-existing name for the vector of partial derivatives of a multivariable function f. So I'm just going to define the vector whose coordinates are the various partial derivatives of some function. I'm going to define that to be what we call the gradient of a function. I'm doing this just so that I can rewrite this expression as a dot product. That's my only motivation here, right? By the way, if you have previously seen the gradient vector and you know some other things about it, try to forget that for the moment. We're going to develop those ideas, right? I'm not making an argument about the gradient here based on other features of the gradient. I'm just wanting to rewrite this expression, so I define this to be the thing that allows me to rewrite this expression. That's all it is, right? This is just a notational choice. So making this definition of gradient, these factors here are literally just the gradient of f evaluated today. So notational shorthand. Yes?
And the gradient is a vector?
It's a vector. That's right. It's a vector with these coordinates. Yep. Okay. So this is what we're going to work with in practice. By the way, we will have much to say about gradients later. But for the moment, gradient is just a notational convenience. Yes?
Is L and F essentially two different functions?
Oh, yes, f is some function that we're interested in, and L is our attempt to mimic f in as convenient and simple way as we can. Yeah. So L is an approximation of f. That's what we call it, our linear approximation. Okay, so let's do one. This is very plug and chug. Here's the formula that we're going to be plugging into for the linear approximation. Here's what our answer is going to develop into as we do the plugging and the chugging. And this is pretty straightforward. The value of f at a works out to be 5 because f is that function and a is this point, and if you take that point and plug into that function, you get 5. So straight up plug and chug, no tricky curves. Okay, next, let's talk about this gradient here. Let's see, I'll use dark. How do I evaluate this gradient? Well, first, per that formula right there, I need to compute the various partials. So partial derivatives of f. Next, we got to plug in this point A, right? So I plug that in to those expressions, and then out comes my gradient. Ends up being 2, 4. Again, that's just what you get when you take the appropriate partials, plug in the appropriate point. Those are the numbers that result. Make sure you can do that, by the way. Right? So one of the risks of class where I do the presentation on the board and everything's already kind of written down is that you can kind of use the pre-existing lecture notes as a little bit of a little mental crutch, right? And it is very important as we go through this stuff to make sure not just that you can follow someone else doing it, right? Make sure that you can, with a clean sheet of paper, actually do it yourself, right? So make sure you give yourself plenty of practice on this, and don't get too comfortable just sitting back and watching. Right? Okay. All right, and then the very last part of this, again, let me just try to clean up my mess here. Last part is I got to dot that with x minus a, And there you go. A is 1, 2. So, okay, very plug and chug. Now there is a question as to, should I take this formula that I just got? Should I multiply it out and collect terms and combine it all together and make a really compact, efficient little formula down here? And I think this is a non-trivial question. Yeah, it's easier to read. This is true. That is what. If I had to program it into a computer that was going to do a couple trillion calculations or something like that, of course, I would want to streamline that as much as possible. But from a analytical point of view, I like being able to see that there's a dot product. I like being able to see what the gradient is. That's information. I don't want to hide that information. I like being able to see the point 1, 2. I like to be able to see the action of the dot product. There's some good information that is visible, right? That you can just see right in this form. And when you multiply it out, that all gets lost. So I think a pretty good case can be made. You just leave it like that. Unless you have an explicit, like we're literally going to be building a bridge. I need to cut the boards. I need to know the numerical value. Okay, yeah, then start multiplying stuff out. And short of that, there's an argument for leaving it in a recognizable form. Yeah.
I'm sorry, could you keep the y minus 2?
Yeah, right. So we got to keep in mind what this is this right here. Right, so the coordinates of the x vector are x, y, and the coordinates of the a vector are 1, 2. So when you take the vector x minus the vector a, the coordinates subtract by coordinates. Is that cool? Yeah. Cool. Okay. All right. Now somebody pointed out very well, very appropriately, that this was for real valued only. But nevertheless, this was a big step because we've addressed how to deal with a multivariable. Okay, sure, still real valued, but nevertheless a multivariable real valued function, and now we know how to do those linear approximations. Now let's consider the full-on problem of how do you do it for not just multivariable, but in fact vector valued multivariable. Right, the most general case that we're gonna consider, and I'm gonna go straight to the notational convenience because there's too much to write down otherwise to suit my purposes. Right? So here's the notational convenience, and this just is what it is. But here's the formula. This is called df. It has another important name that we will talk about later. I don't want to say that name right now because I want to be able to justify it before I say it. So I'm going to do my best to restrain myself to not say the word that I know that it is, but I don't want to reveal just yet. So for the moment, we're going to call this df. This is the thing that makes it all work. This is the thing that fits into the formula that we're going to find has the desired properties of mimicking f in value and in partial derivatives. And let's make a note here about its structure. Notice in the first column of this matrix, it's all partial derivatives. That's easy to do. All the elements are partial derivatives. Right? That leaps off the page. But in the first column, notice that all the partials are with respect to x1. In the second column, all of the partials are with respect to x2, etc. Right? So, very important structural point about this matrix. You're going to make sure that you get this straight. It's so easy to get it backwards, so please put in the effort to make sure that you get it right. Columns correspond to input variables. Specifically, columns correspond to which input variable are you taking the partials with respect to. Okay. All right. Now, the rows also have a pattern, different pattern. let's look at this row right here, the first row, and we're taking partials with respect to x1, x2, x3, etc. It's a bunch of different variables. This does not correspond to any particular input variable, but I'm taking the partial of the first output variable consistently across this row. So rows correspond to output variables. Columns correspond to inputs, rows correspond to outputs. That's the pattern. And if you get it, if you switch those, you're transposing the matrix, and it's not just that it's wrong, it's that it will not do this job. So it seems like a superficial problem, but it's not. It's a your bridge will fall down problem, right? So make extra sure that you remember which way goes which. Okay. All right. Okay, and with that noted, again, here's the formula. This is the linear approximation. Y'all can check for yourselves, can and should check for yourselves that it's got the same value as f at the point A, that it's got all the same partials as f at the point A. And again, this is something y'all can explicitly crank out. Now, I will recognize that, in general, there's a lot of terms and it's a lot of bookkeeping annoyance. So I don't suggest that you necessarily do this for the general case. What I think would be a perfectly reasonable stand-in is do this for, let's say, a function, let's say from R3 to R2, right? And then your matrix only has 6 entries. That's not that bad, right? So write this down for n equals 3, m equals 2. Write down the matrix. Write down this linear approximation. Multiply out the whole thing and confirm that all 6 of the partials do what they're supposed to do. And I think you'll notice the pattern. If you're careful in how you write it down, you'll see how it works. And you probably don't even have to do all 6 to see the pattern and be convinced that this is going to work. Was that a hand or no? Okay. All right. Okay. All right. Good exercise. Again, plug and chug. Let me try to get this all on there. I'm going to be quick with this one because it's not that different from what we've done previously. That is what we're going to write there. And notice we need to compute the value of the function. Well, the value of the function is a vector because it's a vector value function. Okay? So that's how vectors work. And then, so that's just plugging into the, plugging in this point into this function, and that will give that is this. Okay, next. We got to compute the derivative matrix. And again, there's a multi-step process here. The derivative matrix is a bunch of partials. Make sure you can take all of these partials. And you got to think about how they're organized. Again, very important. Don't transpose it. Right? Make sure you organize it the way it's supposed to be. Otherwise, it won't work. You'll get garbage. So you take the appropriate partials. We plug in the appropriate point here, 1, 2, and altogether then our DF matrix ends up being this right here. And again, it's just a matter of plugging and chugging. Okay, make sure you can do that. Okay, all right. A couple of quickie observations. We've already kind of talked about this first one. The columns correspond to an input variable. The first column is all the partials with respect to x1. This is the highly believable, I hope, restatement that I can view the entire column as being the x1 partial of the entire f function, the vector valued f function. So you just compute the partial derivatives one coordinate at a time. Of course, you get all the corresponding x1 partials of the coordinates. It's exactly what you would think. I just thought that ought to get said. What is not immediately obvious and doesn't immediately leap off the page at you, though, if you look over here at the first row, that is a bunch of partials of f1, f1 being a coordinate function, f1 therefore being a real valued function. And in fact, we're taking all of the partials of this real valued function. Where have we heard that phrase? All of the partials of a real valued function. That is the gradient. That's what a gradient is, right? So it's just kind of a neat observation to make. The rows of the DF matrix are all gradient vectors of the coordinate functions. So, kind of cool. All right. And then let's see here. Lastly, so I made this observation that L is not linear, right? It's weird because it's called a linear approximation, but it's not linear. It's very unfortunate terminology. So why do they call it linear when it's not linear? Well, okay, it's a legitimate gripe. But if you look at the formula for L here, I mean, this is what I'm going to call the easy part right there. You're just adding f of a. Right. Most of what's interesting about L happens right here. Right? Most of it is this action of this matrix. Matrix being multiplied by a vector. And if you ask yourself, okay, well, what do you get when you make a function by multiplying a matrix times vectors? You get linear transformations, literally linear transformations. So L is not linear, but DF is linear. And since, again, DF is doing the heavy lifting, most of what's happening is what DF is doing. The term is tolerable. Okay. All right. Okay, last thing we'll do today, and then we'll call it a day. We're going to talk about, eventually we're going to develop tangent planes, but let's start with a flashback to single variable calculus. And y'all remember, here's this function right there. That's what we've called our linear approximation. In Calc 1 classes, my experience has been that they are very often sloppy about the distinction between the linear approximation and the tangent line. In fact, I'll bet you that you have either heard someone else or perhaps have even yourself called this the tangent line. And that's not right. Now again, when you're in Calc 1, it's you can get away with that little math crime. It's because everything you're looking at is a graph, and so who really cares? Right? But I got to remind you, we are not in such a circumstance anymore. Not everything is a graph, and we cannot conflate functions with their graphs. A graph is just one of many pictures that we might ever draw. So we want to distinguish between this function called the linear approximation, this algebraic object, versus the graph, what I get when I set that function equal to a new variable and interpret it geometrically. That is the tangent line. So the linear approximation is a function. It is an algebraic object. The tangent line is the set of solutions to an equation, very special particular equation. That is a geometric object. So let's make a point of distinguishing between a function and its graph, aka between the linear approximation and the tangent line. Okay, now with all that in mind, you notice the tangent line has this nice feature that it kind of, it's like you have a line that just kind of touches there and is kind of tracking the purple curve as much as possible, right? It's kind of mimicking that purple curve. So something very analogous happens when you look at a function of two variables. So here's the two variable case. Notice two input variables. As usual, I'm visualizing the domain as being the xy plane. Okay. And with that noted, Let's see here. Let me get my colors straight. This, again, that's our linear approximation. We wrote this down a couple pages back. That's the formula that does what it's supposed to do. It's a function. And its graph is the tangent plane. It's this plane that kind of, not only does it touch the graph of the original function in just that one point, but it also kind of is oriented in space. It's this kind of a way to kind of mimic how the graph of the function is oriented in space. So kind of an analogous concept to tangent line. Again, it's the graph of the linear approximation, and this is a good place to draw the line. Y'all have a great weekend. See you later. Don't forget to come talk to me if you didn't get checked off on attendance.